Hi all, welcome to yet another blog establishing a hybrid data plane between this time an OpenShift cluster which is running on premises and a EKS cluster which is running in the AWS public cloud. And how do we bridge this divide is through the PowerFlex software-defined storage, which can become the hybrid data plane, the OpenShift cluster, and the EKS cluster. Now, the use cases for such a hybrid data plane could be multifold. It could be disaster recoveries, it could be migrations across what generally in Dell we refer to as ground to cloud or cloud to ground. Now, this phrasing, again, like I said, can express itself into different use cases depending upon your business and technical requirements. For now, allow me to share what we are going to do through the course of this demo through a practical hands-on exercise. Okay, let me share my screen. And you would see, this is what I was talking about, right? What can possibly be a common bridge between these two disparate entities, and this notion of having cross-platform and cross-cloud, one running in private cloud, another in public cloud. The ecosystem or the platforms are different. One is EKS, second is OCP. So let's delve into the actual use case here. I have two PowerFlex software-defined storage instances, one running in AWS and the other one is running inside of my data center. Now, in my previous blogs, I've already highlighted and showcased how we can deploy a PowerFlex or how a PowerFlex 4.5 software-defined storage is at the core of what we call in Dell as Apex block over AWS offering. Okay, this offering at the core of it is again the PowerFlex 4.5 software-defined storage. And in my previous blog, I've already showcased how through a CSI, a container storage interface, we can integrate an Amazon EKS cluster with PowerFlex 4.5. So I already have this set up from my previous blog, and we'll establish the baseline as we talk through this demo or walk through this demo. So this setup is already there. Now, at the other end, I have my PowerFlex software-defined storage, again running on premises. And this time around, on the left-hand side, we have an OpenShift platform. Now, OpenShift platform, you could have, in its own realm, or you could have what is called as an Apex cloud platform for OpenShift from Dell, which is essentially a bare metal offering, and has a full stack vertical integration from an OpenShift standpoint. So it's an end-to-end offering. Regardless, you could have an OpenShift as in a regular version or an Apex cloud platform for OpenShift from Dell. And then through the CSI, it's basically consuming the block storage from the on-premises PowerFlex 4.5 software-defined storage. So this is the setup. Between the two, endpoints, we have an AWS Direct Connect that facilitates high-speed connectivity. Okay, and what we are going to do is establish step number one is to actually, once we set up our application, which is going to be a MySQL workload, a persistent workload, and we will dump in some dummy data, sample data. Post that, we will basically establish what is called as a native replication within these two or between these two PowerFlex instances. Now, given the strength of this replication, one point very important to highlight it, it's not based on a snapshotting mechanism. This comes true this comes in the form of a true journaling based replication, which is far more efficient and real time as compared to snapshotting and things like that, or snapshot shipping, what we call in the industry. So this is going to be a real time replication. Again, depends on your use case. You could the replication is bidirectional, but when we establish the peer connectivity, we create something called as a replication consistency group. A replication consistency group is either a volume or a set of volumes which can be paired across these two PowerFlex instances. Okay. In this case, the instances happen to be in public cloud and on-premises. You could also look at scenarios between two on-premises or co-location and on-premises or whatever. It really depends upon the compatibility of the PowerFlex software-defined storages, saying that they should be compatible and at parity, basically. So location doesn't matter in that sense, okay? So this is basically our use case. We are going to run the MySQL database here on the EKS cluster. The data directory of the MySQL will be persisted over a volume within the PowerFlex array running as Apex block for AWS offering. And then we will be replicating this volume over this peer connectivity over here on the on-premises PowerFlex array. And then based on a real situation or a triggered scenario, you could basically cut over from this instance or this application or MySQL instance to running a MySQL instance here in OpenShift and then consuming this volume. Okay. Now, like I said, this could be a disaster recovery, this could be a repatriation or a migration or whatever. And then this basically, illustrates a cloud to ground kind of strategy. We will also look at how we can reverse the flow from a on-premises to the public cloud, so that I don't want to create biases saying that, this is the one way, and then, we can't actually look back to actually moving on-premises workloads to cloud in case of a on-demand cloud DR or whatever actually may be the reason, right? So the replication can happen both ways, and we will see that in the observed scenario. How do we actually, execute this? So let's go ahead with the actual demo. First, by establishing the baseline of what's there in play, and hopefully you will get to understand the nuances of the setup also actually. Let me move over to this screen. If you look at this particular screen, I am logged into the on-premises, or this is Equinix hosted. So, okay. So co-located PowerFlex, which resembles the on-prem side of the world. You can look at the console or the GUI here. There are 3 hosts. Forget this one. There are 3 hosts, SDC, whatever number, 4, 5, and 6, with these IP addresses. And these 3 nodes, or these 3 IP addresses or the SDCs, they belong to my OpenShift worker nodes, which I will just show it to you now. Let's see the IP addresses: 147.218 and dot. Not this one. Yeah, 218, 147, and 219. So these are the 3 hosts which belong to my OpenShift cluster. Let's look into my OpenShift cluster and validate these IPs: 219, 147, and 218. I am in my OpenShift console. This is running alongside the PowerFlex software-defined storage. Let's go into the compute nodes, and you will see here, let's look into one of the worker nodes, and you can see the IP is 147. So we've got 147 covered. Let's look into the other worker node, and this is 219. So 219 is covered. And the last worker node, which is 218. So 219, 218, 147, right? And that's what we saw here. You can see them here. Also, this particular cluster of OpenShift already bears the CSI integration with the PowerFlex array. So we can look at the storage. Let's look at storage classes to start with. So you can see that there is a storage class called as VxFlex OS. This is the predecessor name of PowerFlex, VxFlex OS. So this is the storage class, and this storage class basically, let me show it to you here, leverages the provisioner, which is CSI VxFlexOS.DellEMC.com, which is essentially the CSI driver for the PowerFlex array. Okay, so if any volume created using this storage class will actually land up on the PowerFlex software-defined storage through this CSI. Okay, now this is the, let's say, the on-prem side of the world. Let's look at the AWS side of the world. Okay, so let me go into my other PowerFlex console, which is here, and this is the software-defined storage of PowerFlex hosted inside of AWS. And you can see that, forget this one, there are two, oh sorry, forget this one, this is his other client, but these two nodes, 172.26.2.9 and 172.26.2.185, they belong to an EKS cluster, and that EKS cluster is registered as a software-defined client to the PowerFlex array, which is running inside of PowerFlex software-defined storage running inside of AWS. Okay, let's validate this as well. I'm going to go to the clusters here in my AWS console. This is the cluster that we are looking at, EKS-Apex block test 1. So let me look into this particular cluster and go to compute. And if I go to compute, you will see 172.26.2.185, 172.26.2.9. Let's validate this again, .9 and .185, .9 and .185. So in fact, I'm trying to kind of make sure that you understand the sequence of the setup itself or the environment itself, so that when we start the demo, it's basically easier to comprehend, these variables in play. So we've looked at the OpenShift side of the house. Okay, so let's also look at the let's also look at some of the resources here which are set up. So let's look at the storage here in the EKS cluster. And if you look at the storage classes here, there are two. Now on the AWS side of the house, I've just kept it as PowerFlex-SC. I've just changed the name of the storage class. On the on-premises side, it was called as VxFlex OS. Doesn't matter, it's my own verbiage or term. I could keep it as VxFlex OS also here. So this is the storage class, which is basically using the CSI integration with the PowerFlex software-defined storage, which is running in AWS. You can see the same provisioner as we saw on premises also. See, the provisioner is same, CSI VxFlexOS.DellEMC.com. So any particular persistent volume created here in EKS will show up here on the PowerFlex software-defined storage in AWS through the CSI integration. Any persistent volume created here in OpenShift will show up in the PowerFlex software-defined storage running on premises. Okay. Now, if you understand this setup and we are clear with it, we will now move to creating what is called as, a volume. A volume would be basically, this will act as the resource to host our MySQL database on the EKS cluster as such. Okay. Now, before we go there, let me just tell you that there are two ways our CSI integrations support volume creation: dynamic provisioning and static provisioning. Both are possible. I'm going to go for ease of understanding and comprehension. We will do the static provisioning part so that you can understand the step sequences here. Okay, so let's go ahead and create what we call as a volume. So I am in the PowerFlex GUI of AWS here. Now, again, volume creation can be done based on a role. Let's say I'm using a GUI here. You could use a Terraform to provision the volume. You could use the dynamic resource method also to create the volume. For now, I will stick to the GUI part so that you understand, like I said. So let's create a bare bones volume, and let's name it as, let's say, AWS, or let's say MySQL volume. Okay, I'm gonna keep it as 8 gig, just a demo. In my previous blogs, I've already mentioned the benefit of actually having the thin provisioning on AWS from a volume creation standpoint, so that you can optimize your costs and planning and things like that. So I'm going to keep it as thin. I'm going to put it into a storage pool, which is a terminology used by the PowerFlex software-defined storage. And I'm going to create a volume here. The volume creation basically results into a volume ID. You can see this volume ID here. Okay. And this volume ID I can then use to create the persistent volume inside of my EKS cluster. So we will do that now. Okay, so let me take this volume ID. For now, I will skip this presentation. I will go here. You can see that this is a YAML template. And this YAML template has 4 resources mainly: a persistent volume to be created, a persistent volume claim to be created, a service for the MySQL so that we can access it, and then the deployment for the MySQL. Okay, this is about it. I mean, it's a very simple use case, but the implications can be very powerful in extrapolating these use cases from a wider enterprise standpoint, right? So I'm gonna do just a quick replace here of where is the handle. Yeah. So I'm going to replace this term volume ID with the actual ID, so that we have the volume inside of the PowerFlex software-defined storage running in AWS. This volume will be mapped to the CSI basis through this resource called as persistent volume, used by the claim, and then eventually mounted on the MySQL pod there. Let me take this particular YAML. Okay. And then I will go to my terminal here. Clear this for now and create a file, let's say aws.yaml. Anything. Okay. And note that the namespace demo, everything is going to come up in the demo namespace. My demo namespace is already created. So if I look at kubectl get ns, you will see the namespace is already active here. Okay. Let's go and create this particular resource. Okay. kubectl create aws.yaml. In that YAML, there are 4 resources. One of them, the persistent volume resource, has the volume handle as the volume ID, the empty volume that we just created, in the GUI of PowerFlex. Okay, so you can see that the 4 resources are created. Let's validate if the MySQL pod has come up. Okay, the container is still creating, which means there are things happening in the backdrop. Now, while this happens, I will also show you the peering perspective that we need to establish between these 2 hosts. Okay, and we will do this in a practical sense, but let me show it to you here. If you look at this tab called as protection, and the same exists here, protection. you can see that there is a peer systems definition. As of now, there are no peer systems, which means that these two software-defined instances, they are not talking to each other. And by virtue of a few simple inputs, it's as easy as 1, 2, 3, and then we would have a peer connectivity. As long as there is a reliable network connection between the two instances, which in this case happens to be direct connect, you could simply create this peer connectivity between the two, and this peer connectivity, given the nature of PowerFlex, it's a high availability, highly redundant kind of stack with multiple nodes running in the cluster. We could establish the peer connectivity as a set of redundant connections actually through various IP addresses actually, which represent the software-defined replication endpoints actually in PowerFlex. We'll come to that. Let's go back to our. Let's see if the pod has been created. You can see that the pod is already created, which means two things have happened. The MySQL, obviously the instance has come up. Second, the CSI driver is working perfectly, because if the CSI driver was not working, then you would not be able to attach the volume to the MySQL pod, and hence the pod creation would fail actually. Okay, so let's understand that. Now, since the MySQL pod is running, what we will do is we will employ some dummy data into this particular pod or into this particular MySQL instance. So to do that, let me manually, we can do this through a typical GUI of adminer and things like that. I don't want to complicate it. I want to focus on the CLI. Make sure you understand it. Let me exec into this particular pod of MySQL. This is in the namespace demo. Okay. So we are inside of the MySQL pod now. You can see that I'm logged in as, into this MySQL instance here. Now, into the pod. Now I'm going to log in into the MySQL instance itself using the username root. And for the YAML, I had put the password as a fake password. So let me use that as well. So you can see that we are inside of the MySQL instance now. Okay, on the pod that is running on the EKS cluster and then persisted through the PowerFlex software-defined storage running inside of AWS. So let's create a. So let me see what, this is a default, right? So show databases should yield all the default values. There is nothing in there. So we will say, let's say create database. Okay, and let's name the database as cars. I'm going to put some dummy data of some car models and whatever. It could be anything, right? It's a database. So let's create this particular database. Let's pick this up, use cars. Okay, so now our database context is basically the cars database. Let me pick up a dummy data set. I've already kept it here ready for our demo. It's about 44 entries of some car models and things like that. So let me take that and put it here. Okay. So we are inserting the sample data. Okay. And then let's see if the data now exists in this particular table called as car. You can see that there are about 44 rows with different car models or whatever. So basically, there is some data inside of this MySQL database. And this data by virtue of the PVC and PV, now resides inside of this particular volume, which we had created and mapped it to the MySQL database. So this particular volume now hosts that data of the MySQL database. Okay, so this is good. It's a very potential use case on its own, saying that you could run EKS, and we've had a blog on this. You can run an EKS cluster in public cloud with Apex block over AWS in the form of PowerFlex software-defined storage. You can run your data on Kubernetes, or what AWS now calls as specifically as data on EKS. It's a new term that they have started using, AWS has started using to signify data on Kubernetes. And that term has been leveraged by AWS to say data on EKS. You could run EMR, you could run any kind of databases or data services. So this in itself, what you just saw, is a very powerful use case. But that's not the story here. Now, we will go into creating what we call as a peer connection between the two entities, which is the software-defined storage running inside of my own environment, and then the AWS. Okay. To start with, we go to peer systems, and then let's say we add the peer system. So obviously it asks for a name. It's just a context. So I will say, let's say Equinix 1. Okay. There's a particular system ID of the remote peer that I need to grep and then insert it here and I can find it out from the system values. For now, I've just kept it handy and ready here. So the Equinix side of the PowerFlex software-defined storage bears this as the system ID. So I'm going to take it from here and put it here. Okay. As far as the IP addresses go, the IP addresses of the remote system are the metadata managers or the SDRs, we call it. SDR and stands for software defined replication endpoints. And you could have multiples of them depending upon what is the level of replication and redundancy in that you desire. For now, I have 3 SDR endpoints, 10.204.111.85. So I say add IP. 10.204.111.86. Sorry, 86, add IP. 10.204.111.87. And I say add IP. So you see that just by giving this particular input set, I can then reduce so that I can make this visible a little. Oops, what happened? Did I cancel it? Chance? Okay. Equinix 1 remote system peer ID is this 10.204.111.85. Add IP. Sorry for this. And by the way, you can do all this. I'm doing it through GUI just to kind of make sure that you understand. You can do all of this through, the API calls and the CLI and whatnot. So it's really very friendly in that sense of infrastructure as a code. So no need to go through a GUI always, but so that you understand, GUI is always better to understand, right? Comprehend better. So we've added these inputs, the name, a context basically, the remote system ID, and the 3 IP addresses. And we will say add. Okay. Now, this is one end. It's like, how do you do VPC peering in AWS, right? It's the same thing. Now, at the other end, too, I will have to make sure that I define the peer so that my Equinix PowerFlex cluster here. Now we'll have a corresponding entry for the AWS PowerFlex cluster. So I name it as AWS1. I take this is my system ID for the PowerFlex side of the world, for the AWS side of the house. And then the IP addresses there are 172.2.124, 172.26.2.125, and 172.26.2.126. Okay, let me show this to you as well. Where do these IP addresses are? I mean, let me show it so let's go to EC2. I said, right, PowerFlex instances running inside of AWS. So let me do that as well. PowerFlex 45 storage. Okay. So you can see that there are 3 nodes here, which are the software-defined storage of PowerFlex running inside of AWS as EC2 instances. Let's see these IP addresses because I want to make sure that you get the corresponding values understood correctly. So 124, 172.26.2.124, 172.26.2.126, and 172.26.2.125. And that's what we are doing here in the Equinix PowerFlex cluster. We are saying that let's establish a peer with some name with this remote system ID. And these are 3 IP addresses there. Okay. We've already done so on the Equinix side of things. The AWS end of the equation, which is the PowerFlex cluster running inside of AWS. We're now doing this at the Equinix side. So now you can see that the moment I did this, if the IP connectivity exists, the firewalls allow the port number 7611, which is the default port. You should be able to see, and if your system IDs are correctly provided as an input, you should be able to see a peer connectivity between the 2 systems. Now, if this is the case, the state is showing as connected. The next step obviously would be to create what we call it as a remote consistency group. Okay. So now, for now, you can understand that you have one volume here. Yeah, there's a volume here with a volume ID mapped to a PVC inside of EKS as a MySQL database with some dummy data of 44 lines. Okay. Now, what we will do is we need to replicate this volume at the other end in Equinix so that I can rebuild a MySQL pod through the CSI integration of OpenShift with PowerFlex. There are 2 ways to do this. Either I can manually create the volume at Equinix end and then do the pairing of the volumes, or PowerFlex in this case allows me to dynamically create the correspondingly paired volume at the other end. We'll see that particular case also here. So for now, we have the peer systems. So the peer is there already. Okay, so peer systems, peer on both ends says connected. Let's go and create what is called as a RCG. Okay, add RCG. Let's name it as AWS-Equinix. I can have a range of RPO depending upon my business/technical requirements. So I can play around with these timers. So the recovery point objectives can be really kind of, met. Now, the source system in this case will be local. I am right now on the AWS end of the, or in the AWS cluster of PowerFlex. And the protection domain, it's a term used by PowerFlex. It's default, we use it. And in the target system, you can see that the target system peering has already been automatically been picked up by the add RCG menu here. So I'm going to select Equinix 1. Target protection domain will also be default. Next. Now, this is what I was telling you, that if I already had a blank volume at the other end, I could simply say manual provisioning and select that volume. Through the peer connectivity, it discovers or auto discovers all the volumes at the remote end. Okay, that can also be done. Here, there's a better way to do it if this is a greenfield approach, auto provisioning, which means that for every volume that we pair, a corresponding volume will be created at the peer end. This saves time from a replication standpoint and the administrative burden that could be put. So let's select auto provisioning. Since there is only one volume, I am seeing only one entry. If there were 100 volumes, I would see 100 entries. So it's my prerogative to select the right volume, which one I want to add to the replication pair. Now, note that an RCG is a logical grouping. So it's not only that I could have, let's say, /data, /log, /this, and there could be 4 volumes for a application set, and then 4 corresponding volumes at the remote end. I could add all 4 of them, these 4 pairs, in a single RCG basically. Okay, and that's again a beautiful aspect that we can observe in the schema of how effective this whole peering and replication arrangement is. So let's take this particular volume, and at the other end, we are going to select the storage pool default and then add the pair. Okay. For now, you don't see the target volume because it's not created yet. If you had this manual provisioning as the option selected, somewhere here, you would see the list of correspondingly target volumes that you could select and add it to the pair. For now, this is auto provisioning, so we will go with the mechanism. So you can see that MySQL volume, 8 gig, storage pool is default, the volume at the target is undefined, thin provisioning, blah, blah, blah. Add and activate. Okay. You can see that the RCG was added. You can see that there are different states it will move through, basically, from a inconsistent to a partially consistent to a fully consistent. So now you can see that the state has gone to a consistent. Again, it depends upon the amount of data you have in the volume, which means more time. And then how is your network? Okay, the reliability of the network in between. So either ways, in this particular demo, you can see that the RCG, which has one volume pair and exists between the peers that you just know of, has now a RPO of 1 minute 60 seconds, that is, and now the RPO compliance is 100%. There's some lag depending upon how things are, but overall, this is the state that we are looking for. So it's fully consistent. Okay. So just from an observation standpoint, one should infer at this point that the 44 rows that we inserted in the volume or in the MySQL instance in AWS EKS persisted over the volume here at AWS end. Now, though, that data or that 44 rows should have been replicated at the other end in a volume pairing mechanism through the peer system. Let's see if the volume has been created or not at the Equinix end first. So I already have one volume from some previous exercise. You can see that this particular volume, you can correspondingly see the time. It's just created. So we are on March 7th. Okay. 5:59, 16 a.m. Time is 6:01 a.m. Right. So this is the volume. And you can see that the name is also the same as the source name, basically. Okay. So the volume has automatically been created. It bears a volume ID. And that volume ID essentially means that I can now create a target PVC and PV combination with a MySQL pod in OpenShift, consume this volume ID in a volume handle, and rebuild a database in OpenShift. Okay, let's see that. How do we do that? But why would you do that and when would you do that? Okay, that is also very important to know. So if you look at the protection menu here, now that you have the volume and the data, perfect. And as you keep writing into the source volume, a real-time replication keeps occurring through a journaling mechanism, which is instantaneous in that sense. Okay, and that means that whatever we write should be available at the target also. Now, when would you need to use this target? Like I said, it could be a disaster recovery. It could be a migration or a repatriation, or any use case that demands that you stop using the source system and start using the target system. So in order to mimic or simulate that environment itself of something going wrong, okay, we can go here to the RCG. So this is the RCG. Let me select this RCG, and you can look at the actions itself. I can failover. I can test a failover also, or I can do a failover, which means the actual, the target volume will become the primary source of data. And then if I want to, I can reverse the entire, the direction of replication. So now the replication is happening from AWS end to Equinix end. And let's say we invoke a disaster and we do a failover, which we will do now. In advent of the target system or the source system coming back online and everything, whatever, maybe it was in a maintenance mode, whatever. Once it comes back online, if you had kept populating your target now with some additional data, you need to kind of replicate that target back onto the source. Okay, so that's reverse. Restore would mean that maybe whatever changes that have to happen in the primary database, they have happened, and then you want to still continue using the primary database in its own form, basically whatever was the original form. So you can do a restore of that. Okay, so now for now what we will do is, before we invoke a failover, let's simulate also a kind of disaster. Okay, let's see this. So let me exit this particular database instance. So I'm back on my terminal. kubectl get pods -n demo. The MySQL system is running. kubectl get PVC -n demo. You have the MySQL PV claim. kubectl get PV -n demo. Oh, sorry, kubectl. Okay. kubectl get PV -n demo. Okay, so we have these three resources and then a service. So let's start deleting things actually to simulate a disaster. kubectl delete deployment MySQL -n demo. Okay, so MySQL is gone. kubectl delete PVC or service, let's say service MySQL -n demo. Okay, so anything regards to MySQL done. The PVC and the PV remain. So kubectl delete PVC -n or MySQL -PV -claim -n demo. So PVC is deleted. kubectl delete the persistent volume, just the reference. The volume itself is there, If this was a dynamically created volume, the moment I delete the PVC, the volume would also disappear from the software-defined storage. But this is statically provisioned volume, so volume will exist. We are deleting the reference to that volume, the PVC and the PV basically. MySQL-PV minus n dem. We don't need the namespace there. Okay, let's delete this. So everything in the source system, the entire, let's say MySQL, all its references are gone. You could be having a MongoDB or Cassandra or anything running there. I mean, and this could be a part of a larger, application footprint as such, right? Running inside of EKS. All that, let's say, is gone. And here we just have one data directory and one volume. You could have multiple volumes depending upon how you have structured your data hierarchy and all that. But everything is gone. Let's say the source system is under duress right now. Now we will go back here. I'm on the AWS PowerFlex cluster. And let's invoke what we will call as a failover. So now you can see that PowerFlex gives you some enhanced mechanisms of either doing a full switchover or a latest point in time kind of failover. For now, we will do a switchover, and I will say apply failover. So now you can see that the RCG is stopped, and the state is in a switchover state. Okay, which means that the source system is affected. The destination or the target becomes the owner in that sense, basically. From you can see it here, the state is switchover. Okay. Now, what I can do at this particular juncture is use this volume, which assume that has the 44 data rows that I can now, it's representative of a data set inside of a database. So I can now resurrect the database in the OpenShift. How do we do that? Let's note the volume ID here. Okay, so this is the volume that is replicated. We'll take this particular volume ID from here. And then I have a YAML. Same YAML, I just kept it different so that we can do a quick copy paste. You can see that this is, I've said, OpenShift YAML. Again, it's the same thing. It's a persistent volume resource, the persistent volume claim, the service for MySQL, and then the deployment for MySQL. Okay, essentially the same thing. Blank database. The only thing that I will do here is take this particular volume ID and put it here. Okay, and you can see that the driver for this particular persistent volume is also going to be, and the storage class name is VxFlex OS. That's just a terminology, but the driver, the CSI driver, is the same for the PowerFlex here, CSI VxFlexOS.com, DellDMC.com. Let me take this particular YAML, no change except the volume ID, and that volume ID is the replicated volume at the PowerFlex Equinix. Let's go to the OpenShift. Okay, and you can see that I already have basically the demo namespace here. Okay, but as of now, there is nothing inside of this particular demo namespace. Okay, now let's go to, let's say, add page, and I will deploy this particular resources through the YAML, which is the YAML that we just edited for the volume ID here. And let's look at it one more time. You can see this volume handle here that I'm pasting corresponds with the volume handle here, which is the Equinix side. This volume is a rebuild or the replicated volume coming from the AWS peering. Okay, let's now say create. Okay, you can see that the resources were created. We will give it a few seconds before the entire process is done. So let's go to the status for the workloads, deployments. You can see that MySQL deployment, there is one pod here and the status is running. Running obviously infers, or one can infer that the persistent volume has been successfully created and mounted on this particular pod actually. Okay, let's verify all of this. Pods, you can see the pod is running here. Yeah, good. Let's also look at the persistent volume. Let's look at the claim. This is the MySQL PV claim, and this is the MySQL PV volume. Status is bound, and then this persistent volume, the status is also bound here, right? So which is good. So now, as of now, in theory or in assumed theory, you have already done a failover. Okay, which means the MySQL pod now should have the volume attached, or it has the volume attached, and then as a result of that, should already have one database. I mean, we created a blank pod, right? I mean, and then mounted. The database should also already be there, which is the database called as cars, with a table called as car and 44 data rows, basically. Let's say that, right? So let's go back to our workload pods, MySQL. Let's go to the terminal here. Okay. And then let's do MySQL -u root -p. Okay, so password is fake underscore password. So you can see that we are inside of the MySQL pod and the MySQL instance running in that pod. If I say show databases, unlike a fresh instance of database, you can see that the cars database is already there. So first step, tick mark, which means the database exists, which means the replication has happened. It's not a blank instance, right? Or a default instance. Now, let's say use cars. And then let's see the data in that particular. Let's see if the table exists or not. So you can see that 44 rows in the set. So the data that we entered at the source system, source MySQL, which is now completely deleted. And then through the replication, we have rebuilt the database. I mean, you look at it, it was so simple. And it was so simple for me to explain it to you. Hopefully you got it. The extrapolation of this capability is something that one can visualize in different use cases. This simplicity can really yield very complex results actually. Okay, so that's the point or the pitch that I wanted to make here actually. Now, think of the scenario, you have failed over. If this was a repatriation or migration, you are done with everything. Yeah, I mean, it depends upon the size of the database and how much time it would take to but you are, whatever time it took, you are already done with it. Given the fact that, the volume was already available to you. So once the baseline exchange happens in peering, all the changes are then incrementally trickled, right? And the volume is always available to you for you to kind of consume or do a repatriation, disaster, or whatever. In this case, the moment I do a failover, I can, kind of start using this database. And from a stateless applications, my microservices or whatever front ends or whatever there is, they can easily be ported onto the OpenShift cluster through the images here. So your application can easily be ported in a very simple construct. Now, if this was indeed a disaster recovery, then we need to switch or do a switch back, right? That's another use case here that we can think of. And that could also mean, let's say, a ground to cloud. Let's say this was the original source system and then target was, in the public cloud. So ground to cloud. So in this case, what we will do is we will make some incremental change on this particular data set. For that, I will take 2 additional entries. Let's say 2 is enough, 20, 200, whatever. I think there's a copy paste. Okay, let's say paste as plain text. Okay, so I'm going to insert these 2 statements into this table, actually called as car, so that the total number of entries becomes 46. So now you have, instead of the original 44 rows that came through from source to target in OpenShift, you've added 2 more in OpenShift MySQL instance, and now there are 46 rows here. Now what we can do is, let's assume a switchover, or you had a fresh instance which you were doing replication from on-prem to cloud, okay? Whichever ways you could look at it. For now, let's delete let's go back here, deployments, MySQL, and delete this particular pod itself or deployment itself, okay? Given that already our job is done. Okay, so this deployment is done. There should not be any pod related to this deployment. We will also delete the service for this particular deployment. Network. So services, let's delete the service also for this deployment. Let's delete the persistent volume. It's the same thing. We're trying to simulate a on-premises failure of sorts, let's say, and bring back the original AWS end of the equation. So let's delete the persistent volume claim. Let's delete the persistent volume. Okay. So everything is gone from OpenShift as well. Now what remains is basically that volume here in the Equinix side. The volume still exists, which now has additional 2 rows in addition to the 44 rows. So total 46 rows. Okay. So let's go here, volumes. So this is the volume, which should now have 46 rows as opposed to 44 because 2 more we inserted. Since the pod deployment, everything is gone, the host mapping is gone. Basically, there is nobody who's consuming this volume as of now. It's idly lying there in the system. Now, let's go back to our AWS side of the house. Let's see. Okay, and you could go to protection, RCGs, click on the RCG, and then reverse. Basically, you are reversing now the replication, which means now this becomes the Equinix side of the house becomes your source. AWS becomes the destination target. We are reversing it because those two entries, 46 entries, now have to be replicated at the AWS end of the equation, the volume which is hosted inside of the PowerFlex cluster in AWS. So we will do a reverse. You can see it gives you a nice graphical view of, all target on the target system will be overwritten. Are you sure? Blah, blah, blah. So replication will start from the current active source to the target, right? So the current active source is the Equinix side. Apply. Okay. So we can see that the changes are being trickled into the Equinix side. So consistency is pending. We'll wait for it to kind of, do a full reverse and write back the data. So let's wait for it for a moment. So it took about 15 seconds just to make sure things come back on. And the state has now become consistent. The thing that we actually look for in such systems is the word called as consistent, right? That gives you a sense of confidence that whatever had to happen has happened. And in our case, we want now the changes which were done when the disaster recovery was in vogue is now done, and we have reversed the flow. Additional data is also copied over. Like I said, this is a full back and forth I'm showing you. You could do this from invert the entire scenario, and you could have your, cloud to ground, or in the other case, ground to cloud also as well, right? Now we have this, the volume ID has not changed. Note that, okay? So it's not a fresh volume that has been created. It's the same volume basically, which has been overwritten with a certain amount of data. So we can simply, and we have deleted all the MySQL and everything here at the AWS end as well, the OpenShift end as well, right? So we can just rebuild the MySQL end, taking, since the volume ID has not changed, I will simply take the same YAML, but actually this YAML already is there, right? So let me take that from the terminal itself. If you recall, cat aws.yaml, we created this YAML to deploy in the starting, right? So this is the YAML. So I will simply go ahead and deploy this YAML back. kubectl create -f aws.yaml. It will rebuild, or it will create the MySQL pod, the service, the persistent volume claim, and the PV, which will be created back from the volume that is already there in the PowerFlex software defined storage inside of AWS. So created, let's wait for the pod to be in running status. So let's see if the pod is now created. Okay, so yeah, about 31.6, yeah. So the pod has now come back into a running status at the AWS end. Let us do an exec into this pod and see if indeed those 46 data rows are there or not. Okay. So we are inside of the MySQL pod. We will log into the MySQL instance. Okay, password. Okay, so we are inside of the MySQL instance. Let's see if databases do show up, or the database cars shows up or not. Okay. So you can see that the reversal has happened. Obviously, the source or the original volume at AWS and already had cars. So let's say use cars. What we are interested is see how much of incremental data has been generated here. From the car. Okay, so I think you can clearly see that now at the AWS end of the house as well, you have 46 rows, which means that whatever incremental data that we had, employed while in a state of failover, 44 plus 2, and did the reversal back on from the on-prem to AWS is now done. So we do have the full 46 row of data, including the original data which was sent over, and then the incremental, during the DI. This concludes the practical demonstration of a simple yet very comprehensive capability that one can think in different scenarios, yielding a proper strategy around ground to cloud or cloud to ground, as I showed it to you in my presentation here, right? And I want to conclude by saying that the things that we've written here in terms of choice, basically it can help you extend and optimize cloud footprints and Kubernetes ecosystems of your choice, number one. Second is the consistency, and you saw that. You can deliver consistent operational outcomes, especially when you have a data. It's not about a cloud first strategy anymore. It's about a data first or a cloud right strategy, and that in that sense, very consistent operational outcomes you can actually deliver, again, regardless of location or ecosystem. Third is the control. You can, because you have two systems which are at 100% parity, you saw the consoles are saying everything is the same. So common governance, common policies, it could be user management or storage management, data management, everything, snapshot management, everything can be unified between an on-premises footprint and a cloud footprint of your data. So thanks a lot for sparing your time. I hope you enjoyed the practicality, as I always say, of this demo. Thank you.